Okay, next, let us see another example. So this example is related to the problem called the knapsack problem. So the input here is we have n items. Let us label them as I1, I2, I3 up to In. Now each of these items has a weight. So Ik, this item Ik, has a weight Wk. And the item also has a certain value. Let's call it Vk. So we have items here. Each item has some weight and has some value. So for instance, this could be a diamond. So the weight is very little, but on the other hand, the value is high. And this could be something like an iron bar. So the weight is heavy, right? So it's high, but the value may not be very, very high. So we have several items here with different weights and different values. And somehow we have a knapsack, a backpack. This knapsack has a weight limit. So the weight limit, let's call it big W. So we can put items inside this knapsack, but then we will require that the total weight of the items that we put inside the knapsack cannot be over this limit, must be smaller than or equal to this W. Now the problem here is we want to select the items so that the total values that we obtain from them is the maximum. So perhaps we will put a diamond inside and some other items inside. So we want to make sure that this knapsack can hold all of them and it will have the maximum number, the maximum total values. Now we may think of the strategies, some strategies like this. So perhaps we will pick the most valuable item first, or we take the so-called densest item. So the item that has the maximum value over weight ratio first. So with the same amount of weight, it has a higher value. So in that case, this is something like more worthy per unit weight. So we will repeatedly either use the first greedy choice or use the second greedy choice to pick items until we will get over the limit, so that in that case we will not take the last item. Unfortunately, no matter you are using the first idea or the second idea, it will not give us an optimal solution. So we can easily construct some input that makes it wrong. In fact, at this moment, no polynomial time algorithm is known to solve the knapsack problem. But for this class, we are not solving this knapsack problem, but we will change the problem a little bit. So the problem that we are going to study is called the fractional knapsack. So here, the items are now kind of a little bit different. So we can think of each item as cakes. So for each item, we are allowed to take any fraction of it. So for instance, this is a cake. Let's say the original value is equal to 20, original weight is 20, the original value is 100. We can take any fraction, for instance, 75%. We take a fraction of it. Then in that case, when we take the fraction, the weight will be changed proportionally. So 75% of the cake will have weight 15, and 75% of the cake will have value 75% of the original, which is 75 here. So in general, for a fraction C, C is a number between 0 and 1 of this item Ik, the weight will become C times Wk, and the value will become C times Vk. And we are dealing with the same problem as before. Items put into the knapsack, but this time we are allowed to take fractions of the item. Now suddenly, we will find out that taking the densest item first will work. So we will leave this for you to prove. This is a greedy choice, right? We can easily show that this greedy choice is correct by using the cut and paste argument, which means that if the optimal does not do the same way or does not make the same choice as you do, then try to do some exchange from the optimal solution into one such that it will have as many densest item as possible or as large a fraction of the densest item as possible. By doing this, we can then get another optimal solution that has the densest item first as we do. So in that case, we will show that some optimal solution will make the same choice as we do. So this is the correctness of the greedy choice. Now, once we have selected the densest item or the maximum possible fraction of a densest item, then we are left with a subproblem. Then we can focus on the optimal solution that must include this item, and so we can apply recursion. So the cut and paste is actually easy to show, so I will leave this for you as an exercise. And also the optimal solution after making the greedy choice can be obtained by recursion is also easy, so you can try to work it out by yourself why this works. Okay, now let us take a look of another problem. This problem is the vertex cover on rooted trees. So let us recall a little bit of what this problem is about. So we are given a tree. We want to place guards on the vertices so that each edge should have at least one guard on it. So an edge is protected if one of the endpoints or both have a guard. So we want to place guards such that edges are protected, but of course, we want to minimize our cost, so we want to place the minimum number of guards in this rooted tree T. So how do we do so? So previously, we have shown that we can perform something like a depth-first search traversal of the tree, and then do dynamic programming and collect the results so that we can find out where to place the guards. But here, we are going to solve it using a different idea. So here, the problem can be solved by DP. But on the other hand, today, we see that if some edge in T connects a vertex U with a leaf, so what do we mean? So this edge connects a vertex with a leaf. So this is an edge like this. This is another edge that connects a vertex with a leaf. This is also an edge that connects a vertex with a leaf. So this is like the leaf edge. So an edge that is connecting a leaf. If some edge connects a leaf with the vertex U, then it is not wrong to place a guard at U to cover this edge. So to protect this edge, one way is we will place a guard here, or we may place a guard here, or we may place guards on both. But we will see that if we place a guard here, then it is already covering this edge, protecting. If we place a guard here, then what does that mean? This guard protects this edge, of course, but if you remove this guard and place it here instead, we use the same number of guards, but then this edge is still protected. So in such a case, this is like the greedy choice. If ever we need to place a guard at a leaf, then we do not place it. We place it at the vertex that connects to the leaf. So this is our greedy choice. So here, this is exactly what I'm reading. And so let's read it again. So the observation implies that we can just place a guard at U instead of the leaf. And so finding the minimum number of guards we will need to do is we will just place the guard at U like this, remove the edges that is already covered, and then focus on finding the minimum number of guards needed to cover the remaining tree. So let's see how it works. So here, this is the example. So this is the U that we have because it connects to a leaf. What we are doing here is we place a guard here, and now this edge is protected. This edge is also protected. So they are now removed from consideration in the computation of the remaining parts, how we place guards to protect the remaining edges. Then if you look at this one, then this is a leaf, right? So this is an internal node. So this is a U that we have now. So what we do, we place a guard here now. Once we have placed a guard, these edges are protected, so we are left with this subproblem. And so this is a leaf, this is a U. So in that case, we will place where? We will place a guard here at U. So in that case, once it is done, then it's done. Now, all the edges are now covered, so there's nothing more to be done. So we are ending. So in the end, we are left with these three guards. Now notice that in the running, the removal of a certain node U. So once we have placed a guard here, we are actually removing the edges connecting to this U. So we are actually removing U and also the edges. So when such a case happens, then it could be like it could give us more than one tree as a result. It could. So for instance, somehow, in general, maybe we are removing this one. We don't know why, but if we remove this one, then we have this part and we have this part. Yeah, consider that there is a leaf here. There is a leaf joining to this one. So if there is a leaf joining to this one, we may pick this one as the node U. So in that case, we will pick this first, then we will remove this part, this edge, and this edge. So we will have this tree and this tree obtained. But it's still okay. We will just treat each tree as a separate subproblem. And notice that this method can be implemented easily with the depth search traversal on the tree T. So in that case, the total time for applying this method is order n. It is the same as the order n time that we were giving out in using the dynamic programming. But here the idea is simpler, and so this is somehow an easier to understand method. Okay, so this is the discussion on the vertex cover on rooted trees.